It's time to do some more fluid dynamics, and in the previous videos we have made a function to calculate the gradient of a field. We've made a function to calculate this quantity subject to this constraint, and in another series we also wrote a function to solve this differential equation for p given the right hand side. So now and we also have a function to calculate this thing. So now we actually have everything we need to solve this equation. We are ignoring these two terms to make it simple here to begin with. So let's try to do that. So we have that dv, and we're just going to write I, where here I can be x or y. But anyway, dvi differentiated with respect to time is equal to minus this thing. So previously we called that fluid term 1. But I think now we're just, so we'll call it ft1. And then there is minus 1 over rho gradient of P pressure. So this thing, this is our equation, and we'll again do some forward difference for this. So we'll say Vi at time t plus 1 minus Vi at time t divided by delta t. Probably it's better to say plus dt. Do something like this, which means that this quantity Vi at the next time, this is the one we're interested in finding, can be written as this plus Vi at time t. Right. So this is the thing we want to compute here, the right hand side. So we're going to need a lot of helper fields and things like that to store intermediate results and things like that. But let's just get started. So let's call it time step. That's maybe a bad term, a bad name, because we also have, let's call it step once. I don't really know what to call it. So it's a procedure. And what's it going to take? It's going to take the current field. So let's call that Vi, and it's a field. It's going to take a time step. Actually, we have this fluid thing. So why don't we try to define it in terms of that? So it's going to take a fluid, which is now fluid 2D. It's going to take a dt, which is a floating point number. And then we're going to need some extra scratch fields, I think. But let's start with this. And it's not going to, maybe to make it more simple, let's do it like this. Fluid 2D, and I shouldn't have had that one. I think that's how you do it, right? Yes. Okay. So let's start by calculating this. Let's start by getting the pressure actually. So let's go into, I think I put it in the fields for some reason. Pressure right hand side. So do we actually have what do we have that involves pressure? We have find pressure. So we never finished this one, which we're gonna need now. So what we want to do is get the right hand side So let's write pressure field, and then Vx field is also a field where the data is just pointing to Vx of the fluid, and width is fluid width, height is fluid height, and dg is fluid dg. So these things, P and Vx and things like that, are slices in Odin. And slices in Odin, they work like pointers. So when I do this, it's just copying the pointer, like when I assign here. So let's also make Vy. Then we need a destination and a row. So do I also have row? Here I do have row. So fluid.row. And I need somewhere to put the right hand side. So I need an extra scratch field. Now the question is, do I put it in here in the fluid struct? Or do I not? Let's put it here. And then we need to update this. And this. What happened to there we go. Then we'll say destination is just, well, we don't need to do that. So let's find the pressure right hand side now, which is this thing. So we need Vx, actually we need a pointer. We need a Vy, we need the destination, which I just said was gonna be, so we actually need to make a field as well. So field to D. Data is the fluid scratch field, and all of this is the same. So destination and the row. I'm going to take this guy and put it down here actually. So now we have the right hand side, and let me remove this debugging stuff. Maybe we can keep it. Let's just move it. Okay, so that's the right hand side taken care of, and now we need to solve it. So we have the Poisson solver here, where we simply say solve Poisson, and we'll put in pressure field and the source, which is in the destination. We need to check one thing, which is the sign. So I think we have a problem, two problems, which is that the sign is wrong. It should be multiplied by minus rho, like that. Right. So now after we've done this, the data should be inside P. So let's try to call this? Don't need all these things. Let's try to do that. So I guess what I want to do is just to make it super simple, let's visualize. Then I need to construct this like pressure field. There's gotta be a better way to do that. Okay, anyway, so there we have the pressure field. Let's visualize that. Let's delay. Forget how you call it. Okay, it's with capital D. Let's delay for 1 second. Then we call find pressure, and then we actually, this one has to go here. This one has to go here. So in the very first iteration through, we'll just visualize the initial field, and then we'll show how it looks after. Let's try to run it, and it did not compile because we have to do that. Apparently there's a problem over here. 7. Okay, for some reason I called them field. Let's just remove that. And I also just called them Vx and V of y, no underscore. Let us do something else also. Let's do some debug printing. Let's say visualized, and let's say delay over. And let's say found. So it's always 0, which is worrying. What happens if I run it in here? Okay, it does update, so we can do that. Right. I think it's because the velocity starts out as 0, which makes a lot of sense. But I thought we had some stuff here. How do we... So we gotta make our own fluid, so that fluid 2D. Which will have a Vx equal to Vx that we make here, some non-zero thing. Let's just make a new array. And what more do we need? We need row, it can be 1. We need field width, field height. Make the scratch field. And then a lot of these things have to be turned into pointers. What did I do wrong? Right. Okay, so it's definitely doing something, and it is not, it kept changing, which is worrying. It should not keep changing, but it's probably because, well, that I'm not sure. Pressure should only depend on the velocities, and the velocities should not change. Let's just check that the fields are not changing. Actually, let's just do it there. Right, I forgot. I just need to check something. So this scratch field should always be 0. So let's say for I in 0 to fluid length, fluid scratch. So it's not that. Is it because this thing is not converged? So that didn't seem to be it. I found the first bug. It says dy, dy, dvy, dy, which is should be x here. Unfortunately, it doesn't solve it. I also printed the final error of the solving the pressure equation. It keeps growing for some reason. Also, the pressure average keeps growing. There was also a bug here. I went over the derivation again. It said dx here, which should have been dy dx. The rest was more or less okay. It didn't fix it, but we're one step closer. Okay, I finally think I found out what happened. There was not a bug in the calculation, but there was a bug in how we calculated the error, like how close it was to converging. Whereas before it was this, which is wrong. It's not xk1 that should be equal to b. It's something else. So this is what you do instead. You check how much it changes, and then you see if it converges. So now if we run it, we can actually see that the error is going down. The field is not changing, so we can do something else. We can do, actually let's keep it and remove that one. So the error is going down, not super fast. And then finally it converges to something. So it's just that it's kind of hard to solve this particular thing. But it's not that the error is that, it actually starts out quite big. So perhaps what we should do just to be sure is to up this one a little bit. What if we make it 2000? No, it's still not good enough. This one can be here. Yeah, so obviously it's quite slow. Let me see something. So it uses 6,000 iterations. And then it's basically converged. So what we should do, I think, is to make sure we save the value in the pressure field between time steps, because that way we can hope that it's close to converged and this won't take very long. But we really need this very high max iterations, because otherwise we saw there could be a huge error. We don't want that. Right, so fine pressure is done now, so this we should not do, because we want to keep the pressure field from the last iteration. Right. And this one should not be called destination. That's a little bit misleading. Let's call it scratch. And here in source field. Great. So where were we? We were doing something. I guess we were here, and we were trying to do this thing. Okay, so let's find the pressure. And it simply takes the fluid. That's nice. So now we have calculated the pressure. Then we actually need the pressure gradient. The gradient is a bit annoying. Let's go here. So then let's calculate the gradient. It takes a field, the field you're taking the gradient of, which is the pressure, but then we need to make it into a field again. like so. We need some kind of helper function for this. So like get field. It takes the fluid and it returns a field, something like that. Let's try that. Actually, we need the fluid and then we need the data. So then we can just say something like this. Okay. So we have the pressure, then we need the destination fields. So then I want to say fluid scratch. That also has to be a field. Get field, fluid scratch. Get field, fluid scratch. 2. Now we need another scratch field. Let's see if it compiles. It doesn't compile because right, and we need also the data, so actually it's this is a horrible API, but I'm not sure how to make it better right now. I just want to make it work. So it does compile. So that's the gradient. Actually, I want to put in an optional factor. Does that work? It works. Because then we can say the factor here is supposed to be -1 over rho. So we have that. Now let's find this thing that we called. Did I put it here for some reason? No. Fluid term 1. So fluid term 1 takes velocity fields. It takes destination fields and scratch fields, which means we need 4 more scratch fields on the pressure, on the fluid, sorry. Something is telling me that this might not be quite right. See if it compiles still. It does not, because of this thing. All right. So then let's call this one, let's rename the test fields to P something. Then these guys we can call dx. And then we need scratch one. Right, so Vx, Vy, test X, test Y, scratch one, scratch two. So far so good. Now I think we have all the terms. Ah, wait a second. So let's say we have two fluid fields, so we can actually half the number of things. And then these are simply from the next one. Okay, but now we have to say for I0, I less than fluid. What are we going to do? We're going to say fluid next at I should be equal to fluid. Actually, Vx is fluid Vxi plus the time step times. And what is this fluid term? I think that is simply this thing with positive sign. So we need minus destination x the data minus the gradient thing. And that's it. And actually, can we do something like fluid temp is pointed to fluid 2D, then we're going to say fluid temp is fluid next is fluid, and fluid is fluid temp. So we swap them, and then let's see if it compiles. It doesn't compile because I forgot to say data I. Cannot assign to fluid, which is a procedure parameter. Right. We could do this pointers to pointers, or we could assign the internal data. Reassign. Let's do this. Right, I see it now. It's this thing. Okay. Right, the get field thing needs the fluid and where to put it. So we have to say fluid next, fluid next, fluid next, fluid, and actually we have to get the internal pointer. Doesn't look pretty, but I guess it works. Because what we should be able to do now is, let's go up here, define a time step, and let's say fluid next is scratch. That's another thing we should change here. Should be called fluid scratch. Okay, so now we need to visualize it. Let's get rid of that. Honestly, get rid of that too. Get rid of that. Let's keep that one because I can never remember how to do it. Okay, so we want to let's try to do it. Let's say step once, fluid, DT, fluid scratch. Let's just try to call it, see what happens. And actually, let's do it like that. So so it failed somehow. So we managed to find the pressure. Okay, let's just put in some debug statements. This one is going to be gradient. This one is going to be ft1. This one is going to be a sine. So we only get the pressure. The gradient fails. Let's move that one. Seems like it could be due to something here. So let's go into the gradient. Let's say field width, width height. Seems fine to me. Actually, it does seem a little bit weird. I guess that's what okay. So that should work. Let me just try again. Then in this one we'll say, instead of field, we'll say destination, and in this one, instead of field, we'll say the other destination. Run that. That is also great. It says 138. Right, so maybe instead of this I should have done field length. Great, so the X, so switch to, so, now I think I know why. It's because here I made it myself, so I never made the scratch too. And why don't I just use make zero fluid? Because we want some And we need to make scratch 3 as well. Okay. It ran. Let's get rid of that. Let's go down here. Let's run it one more time just to be sure. Yes. Okay, it seems to be working. So now we need a way to visualize the field. And visualize the fluid. So let's make a new field. And then we'll say for I and 0, length can I do this? Maybe. The field length is a procedure that takes field and returns an integer, maybe. No, that somehow didn't work. Okay, let's not do that. Let's just do this. Right, and let's put into the field, let's put fluid times fluid let's do that, and then visualize field, take the field and the renderer, and I think it has to take a pointer, so let's do that. Syntax error 35. I don't need that. A little bit tired, I guess. So what happens if I do this? Can I index this field of type? So something happened. It looked cool for a second. Let's not quit it right away. Okay, that looks correct. Let's now try to step every time through here. And it instantly went to 0. That's weird. Let's put in a delay of a second. takes a long time to calculate the field, then it's 0 for some reason, and then the third time around it doesn't converge. Okay. Okay, I guess one issue is that no, this should be okay. It's supposed to be a pointer to a pointer, and this is, I cannot do this, right? That would not compile. What's it complaining about now? Can I take the pointer address off? Okay, I already see one sign problem, which is that here I multiply by minus a negative number, and here I subtract it again. But that shouldn't be like that, it should be like this. So actually, how about we take that one and put it here instead. Let's remove the delay, make it a little bit shorter anyway. First time it takes a long time, and then still breaks. Alright, I finally found the bug. The density of the scratch field was not set, so it was equal to 0. That we should probably do something about that in a better way. But all of this code is very, very messy, and we need to fix it at some point. So if I run it now, it takes a long time in the first iteration as always, but then it starts to go faster. Quite a lot faster. But let's try to, instead of visualizing the density as I was doing here, just to check, let's visualize the squared magnitude of the velocity. I don't know what to think about that. Also, it starts to go slower and slower. Let's have an average here. Let's print that. Average squared velocity. Let's comment that out. See what happens. It goes up quite a lot, which is worrisome. There's probably another bug. Want to try one last thing? I wrote this function that goes around the... Well, that's not what it does. I made a mistake. Okay, now I have this function that goes around the boundary. First at the first row, then at the last row, then at the first column, then the last column, and it sets the velocity to 0. Then I call that here to just see if maybe there was some issue there. If we run it, it does not work. I can spoil you. So I don't know. The colors are a bit wrong. Perhaps let's go into visualize field. Visualize. No. It's right here. It's because blue is high value and red is low value. Let's change that. So now red is where the velocity is very high, and for some reason it like gathers up here. And I'm sure there's some kind of bug. But I think we'll look at that in another video. So until next time.